All right, hello class. Welcome to Calculus 1. And in this first lesson, what we're going to be doing is really introducing limits, but this also acts as a way to introduce calculus. I think a fair place to start whenever we are learning a new subject is talk a little bit about what the topic itself is, right? So what is calculus? Why would we want to use it? What are some of the motivating concepts, some of the motivating ideas? Okay, and so that's what we're going to be talking about in this particular video, along with actually introducing limits, because limits are our first step towards calculus and all of the things that follow. Okay. All right, so what is calculus? Well, I always like to say that calculus is the mathematical study of change. Okay, now I remember teaching this one time and a student saying, well, isn't that what chemistry is? Isn't that what physics is? And yes, I would say most sciences are basically the study of change, how things are changing. You could even argue that that's what geology is, and possibly even biology, in a lot of fields of biology, and psychology, sociology, whatever, history. Lots of things study change. So what do I mean by this mathematical study of change? Well, to put it more specifically, it's learning the mathematical tools required to study how one quantity maybe affects another quantity. Okay, to put it more formally in text here, it's developing the mathematical tools to formally study how the change in one quantity elicits change in another quantity. In other words, how does a change in X affect Y? Well, we've already kind of talked about this before. In your algebra or pre-calculus classes, you've talked about slope, right? So let's start by thinking of slope. Think slope, that gives us the change in Y over the change in X, right? This is the comparison or ratio of changes in an independent variable versus a dependent variable. Okay, so in other words, how does Y change as X changes? Okay, so we've been doing this for a while, but notice what I say here. It's not just the mathematical study of change. We've been doing that a lot. It's developing the mathematical tools to formally study how the change in one quantity elicits change in another. This is a big part of it. It's developing these new mathematical tools to move on to a more formal, right? A more formal, I don't want to say adult, but a more grown-up form of math. Okay, that's what calculus is all about. Okay, so I always think of calculus as our first stepping stone from what I would consider maybe basic math or adolescent math, right? So things like your arithmetic, algebra, geometry, trig. I consider algebra and trig together to essentially be pre-cal. Okay, and calculus, especially calculus 1, but calculus helps us take that step into more advanced math. Okay, which gives us your differential equations, numerical methods, modeling, other more sort of advanced math like maybe vector analysis. Okay, and this also jumps us to the advanced sciences as well. Okay, specifically physics. A lot of physics requires calculus. There's biological models, parts of biology, chemistry, etc. that use calculus in order to operate. Okay, so there's only so much you can do without having the tools, right, to move on to the more advanced sciences, the more advanced mathematics that are required in the STEM fields. So this is really a bridge course. Now, part of that makes this fairly difficult jump. Okay, so a lot of this is you're going to have to accept the fact that a lot of the stuff you did back here early on, say up through high school in your math classes, may not work here. Okay, this can be a tough jump for some people. Okay, so keep that in mind as we go along, that you may have to reevaluate how you approach math classes. I get a lot of students, well, maybe I shouldn't say a lot, but I've had a lot of students tell me that, they've always been good at math up through high school, and then when they get to college level math, suddenly they do really bad. And it's not that they're not good at math anymore, it's that the level has advanced, right? I feel like our school systems, we travel so slowly through this category of mathematics that when we're asked to make that jump through calculus into the advanced mathematics, a lot of us don't have the tools necessary. Okay, so keep that in mind, that this is more than just you're learning a new subject, you're also learning a new way to approach mathematics. So keeping an open mind and being open to maybe having to work a little harder than you have in the past, or accepting that you might have to do a little bit more homework or studying, that's part of it as well. Okay, so keep that in mind as we go forward. So I keep mentioning the tools for calculus. Okay, so the first tool that we're going to talk about is what this whole lesson is titled after, and that's the limit. Okay, so let's talk about our first tool. All right, so before we really learn about a tool, or say if we're actually buying a real tool, before we ever do that, we really need to know, like, what problem are we trying to solve with it, right? What is that motivating factor? And so this bridging idea comes from one of the problems that we've had in math since we started, and that has to do with zero and division. Okay, that's the big math problem we have in, say, arithmetic and algebra and function theory, everything. Dividing by zero is always that problem. Okay, so why is dividing by zero an issue? Okay, I think this is something that a lot of people don't really talk about. You know that you're not allowed to divide by zero, but either we weren't ever told why, or we were, but it was so long ago that we just don't think about it. Okay, but in my experience, most people just aren't even told. You're just told you can't divide by zero. Okay, so let's think about what division actually is. Division, you can always think of division as a sort of pseudo multiplication. So if we think about division as, let's say I take 10 divided by 5 is equal to x, right? I'm trying to solve this problem, right? 10 divided by 5 is equal to what? Well, this is equivalent to this equation here. 5x is equal to 10, right? All I've done is move the 5 over, multiplied both sides of this equation by 5 to get 5x is equal to 10, and x here is equal to 2, right? 2 is the number that would cause this equation to be true. So division is actually equivalent to solving an equation with multiplication. Okay? Now, we start to get into trouble when we divide by 0. Okay, now we can have 0 on the top, right? If we take 0 and divide it by 5 and we say that that's equal to x, that would be equivalent to saying that 5x is equal to 0, and if we solve this equation, x needs to be 0. So 0 over 5, 0 over anything really is 0. That's fine. The problem happens here if I take 10 and try to divide it by 0. Okay? If we equivocate this to, say, its equivalent equation, this would be 0 times x equals 10, right? What x can I multiply 0 by to get 10 out? And the answer is, well, we can't, right? This is nonsense. The second we put any number in here for x, x times 0 is just going to be 0, so there's no x that satisfies this equation. Right? So because of that, that's why we just say that 10 over 0, or really any constant over 0, is undefined. All right? And we've seen this out in the wild before. If you have taken or calculated the slope of a vertical line, this is what you end up with. Okay, so for example here's a vertical line, and if I take 2 points, say this would be the point 5, 0, and this would say be the point, let's say it's 5, 5. Okay. If I calculate the slope of this line, remember that's delta y over delta x. Well, the delta y's, so the y changes, say 5 minus 0, but the x, on the other hand, is 5 minus 5. The x is not changing, so we get 5 over 0. This is an undefined slope. Okay. However, this number is not I should say this number doesn't mean anything, but what's happening here is not meaningless. This is still a line. It's just a line that cannot be written as y equals mx plus b because the m is undefined. Instead, this line has to be written as x equals 5. Okay, it does not fall under the y equals an f of x type situation. It's not a function in the traditional sense, right? It definitely fails a vertical line test. But it's still a line, okay? Even though it has an undefined slope in the y equals mx plus b situation, okay, it's still a line. All right, so this is where we see this happen. It's not the only place, but it's where we've definitely seen it in the past. Okay, now what's even more crazy, okay, and this is where people will mess up a lot. So we know that we can have 0 on the numerator, that just gives us 0. We cannot have 0 in the denominator, that's undefined. What happens when we have 0 over 0? Okay, this is what's called an indeterminate form. We'll talk about that a lot in this course. But if I set this up like I have here as okay, 0 over 0 equals x, let's rewrite this as an equation, you get 0 times x is equal to 0. Well, the funky thing about this particular case is it's not that there's no solution, it's that all x's will work, right? Any x we choose will satisfy this equation, right? So it could be 0. Or a lot of people will say that this is 0, but some people will say it's 1, right? Anything divided by itself is 1, right? So if you remember, 5 over 5 is 1, and that's because if you set that if you make that an equation, you have 5x equal to 5. The only way that happens is if x is equal to 1. So some will say, well, that's 1, or we could say it's 1,000, right? This has infinitely many solutions. Okay, and that's what we mean when we say that this is an indeterminate form, or an indeterminate case. Okay, so 0 over 0 is what's called an indeterminate. And you can see what that means in the root word determine. Indeterminate, meaning we can't be determined without more information. Right? Indeterminate. So in other words, well, that x could be 1,000, it could be 1,000,000, it could be negative pi, it could be 100, it could be nothing. Nothing may satisfy this particular equation given, well, we'll get into that. But indeterminate forms are where the limit steps in. Okay, so this is where the limit shines. All right, because the limit itself is a tool that helps us determine indeterminate forms. It helps us determine the indeterminable. Okay, and it's also going to help us with this guy here, but we'll get into that. Okay, so that is the motivator here, or one of the many motivators here, that the limit helps us deal with 0 over 0 situations. Now note, this is not the only indeterminate form. We'll get into more as we go along, but this is the first one that we're probably fairly familiar with. Okay, so a question here would be, well, where do we find indeterminate forms? And you've probably seen them, but what I want to show is going back to what we did before with slopes, right? The slope of a vertical line. I want to show through slopes of lines where this indeterminate form can show up, but there are lots of other places, and we will get into that. All right, so if we go back to geometry and remember tangent and secant lines for a circle, you may remember that a tangent line sort of hits the circle once, okay, and kind of has this effect of bouncing off of it, right? And not awesome at drawing these in this software, but yeah, a tangent line basically kisses the circle. It hits it once and that's it, whereas secant lines go from one point on the circle to another point on the circle. So they sort of behave more like this. Okay? So what I want to show is that there is a way that secant lines and tangent lines can relate to one another, and that's by coming up with a way to mainly create a situation where the points between this creating the secant lines get closer and closer and closer and closer together to where eventually you are essentially just talking about the tangent line itself. Okay, so let's consider, all right, so we're going to consider secant lines where the points on the circle get closer and closer together. And to start with, what I'm going to do is, okay, I'm going to start with the point. All right, I'm basically going to start with the unit circle centered at the origin, and pretend like I'm doing this well. And I'm going to look at secant lines between the point 0, 1 and other points on the circle. Okay, so say here, here. So we'll start here at 1, 0, and we'll be moving through different x, y points, but we'll get closer and closer and closer. Okay, so we're going to be looking at these lines with slope delta y over delta x, which will end up being, well, we're always using the point 0, 1. So we could say it's maybe y minus 1 over x minus 0. So y minus 1 over, our x. Okay. And we're going to calculate this at different points. Now, here's one thing to note. If this is our formula, I can't just plug this point in. If we were just to plug in the point 0, 1, we would get, well, our x would be 0, so we're already dividing by 0, and then we would get 1 minus 1, so this would be a 0 over 0 case. So we can't just plug this point into the formula. However, if we instead just look at what's happening to points closer and closer and closer and closer, we're going to see something interesting. Okay, so I've constructed an actual graph so you can kind of see what we're talking about here. Here's the point 0, 1. Here's the point 1, 0. We're going to start here. Okay, we don't have to, but that's just where I'd like to start. Okay, now I'm going to let the x and y, and specifically I'm going to let the x get closer and closer to 0 here. So as we do that, okay, you'll start to see that eventually the line starts to actually level off. And what it's leveling off to is actually the tangent line. Okay, so as these points get closer and closer, now let me pause this. One thing to note here. Okay, here we are at the point, looking at the secant line from 0.01, 0.999999, so that's almost 0.1, and we get the slope negative 0.005. Okay, if I take one more step, and notice the slope we get is just a question mark when I'm actually at the point. Okay, so what's happening here is as we start finding secant lines, right, as the x gets closer and closer to 0, the line itself gets closer and closer to the tangent line, and the slope gets closer and closer to 0. Okay, now what I want to do is actually zoom in and get closer and move on a much smaller scale. Okay, so here we are at 0.1 in the x, and I want to get closer and closer and closer, and you'll see that eventually there's almost no difference between the secant line and the tangent line itself. And as we get closer and closer to the point, the slope itself is getting closer and closer to 0. Okay, if I see if I can make it take a smaller step here. Yeah. Okay. Actually, I don't think it will. Okay. All right, so eventually what happens is these secant lines approach the tangent line. So what that tells us is that this y minus 1 over x eventually gets closer and closer to 0. Okay, the m gets closer and closer to 0, even though if we were to plug the 0, 1 in, we would get 0 over 0. So here's a case where the 0 over 0 is essentially coming out to be 0. However, that's not always the case. If we started at another point on the circle, maybe halfway between here, okay, we would find much different behavior. Okay, so suppose we're actually at starting our secant line type thing here at this point, 0.8, 0.6, and we'll see very similar approach here. But what I wanted to show is that we can do it from both sides, and we'll see that here the slopes will start to get closer and closer. I'm calling the red slope N here. But as these points get closer and closer to this one, we'll notice that these secant lines are converging to one another. And what they're actually converging to, well, is once again the tangent line. Okay, so if I pause this and move it to almost its last step here, move it to almost its last step, you almost can't tell a difference between the two lines. Okay. All right, and we can see that these slopes are very, very close together. So notice what we're doing here is I'm taking very small steps of distance 0.001 and getting really close here. Okay, that's what the limit does. The limit is essentially taking a snapshot of what a quantity is doing as it gets really, really close to a problematic value. So here, once again, if we were to actually plug in the point, right, when we do that, we're going to see, if I go all the way to 0, look at what happens here in my my software here. It's showing an infinity and negative infinity. It's essentially confused. If you remember before, it just gave a question mark. Now it's spitting out infinities. What's happening is if we plug that point into that formula, right, so we're essentially finding the slope of the line between 0.8, 0.6 and any xy on the circle. And so the slope of that line is going to essentially be 0.6 minus y over 0.8 minus x. And if we were to actually plug this point in, right, if we actually put in the 0.8, 0.6, we would get 0 over 0. Okay, but notice when we got really close, right, if we got really close to the 0.8, 0.6, all right, let me take a step forward here. The slope was about negative 1.33. Okay, and we'd have to get closer to get a better approximation, because you can see that they're off by a little bit, but we could get much closer. We could zoom in and get even closer. Okay, so here I have zoomed in by a lot, and I can get even closer. And let me... Okay, when we do that, we see we get these two are matching. So here you can see I'm at the point 0.8000001 and 0.799999. Okay, and as we get closer, we can see it looks like we have a pattern here of negative 1.33333. It seems like we keep adding 3's as we get closer. Okay, that's just what it looks like. We would need a lot more. We need more tools to establish this exactly. Okay, but what we can say is when we get even closer, our slope becomes negative 1.3333. Okay, so we can basically assume that the slope there of the tangent line is going to be about negative 1.3. Now, if you were actually to graph the tangent line of this circle at this point, there are a few ways you could go about doing that, but what you'll find is that the slope actually ends up being negative 4/3. Okay? Well, the slope of the tangent line is negative 4/3, which turns out to be negative 1.3 repeating. So as the secant lines get closer and closer, their slopes get closer and closer to negative 4/3. Okay, so while we can't plug in the 0.8 comma 0.6 because that gives us a 0 over 0, which is undefined. Okay, so that little slope formula, m of 0.8 comma 0.6 is 0 over 0, which is undefined. However, the slope of xy approaches negative 4/3 as the point xy gets closer to the point 0.8 comma 0.6. Okay, this is the main idea of the limit. Okay, the limit establishes or describes behavior of one quantity as another quantity gets very close to some value, usually a problematic value. Okay, so this is essentially the basic idea of the limit. The limit describes the behavior of one quantity, in this case the slope, as another quantity gets closer and closer to a specific value. So here we're describing what the slope is doing as another quantity, here the point, gets closer and closer to a specific value, usually a problematic one, usually one causing 0 over 0 cases, right? Usually indeterminate forms, 0 over 0 cases. Now to get back to that indeterminate form thing again, remember we just looked at one case, the first example. We had an m going to 0, which was a 0 over 0 case. And we had an m going to negative 4/3, which was another 0 over 0 case. We saw two possibilities, both coming from 0 over 0. Turns out it can get even crazier. So let me show one more example with the circle. Okay, the last example I'd like to show is what happens when we do the same setup but at a point that has a vertical tangent line. Right, so the tangent line at the point 1, 0, right, is this vertical line x equals 1. Right, that's the tangent line. And if we remember, the slope of a vertical line is a constant over 0. That's when it's not 0 over 0, but constant over 0. Now, if we bring this point in here, let me zoom in a bit, and I start looking at the secant lines between this point and any point close by, and we will see that still, as we get closer and closer and closer, the slope of the secant, or the secant line itself, is approaching this vertical line. But look at what's happening to the slope itself. I just pointed at the screen. So as we are further away, so all the way, say over here, our slope is negative 14, but as we get closer and closer and closer, these numbers get larger and larger and larger. They're negative, but here we have negative 99, here we have negative 141. The lines are getting steeper and steeper and steeper until they are essentially becoming vertical. Okay, so at this particular point, we had a 0 over 0 situation, okay, which if we take it all the way to the end, here it's giving us a question mark, right? It's not really sure what the slope is. But this is a third possibility. We got an m that went to essentially a constant over 0, right? A vertical slope. And that was our 0 over 0 case. Right, so 0 over 0, well, there is a lot of stuff going on with that. Okay, so that is what the limit is going to try and determine for us, is what's happening in each particular 0 over 0 case. Okay? Okay, so now that we've kind of gotten this idea of what the limit is, I'm going to go ahead and put a cut in this particular video, come back in the next one to define the limit and talk about it in terms of how we'll be approaching it in this class. Limits are kind of very broad in their scope and how we can talk about it. Okay, so what I'm going to do at the moment is just cut this here and then come back in the next lesson to talk about the formal definition of the limit. Well, maybe not the formal definition, but how we approach it in a sort of algebra sense, not necessarily a geometry sense. All right, so I will catch you all on that one, but do keep in mind what the limit is doing here. This idea that we're describing the behavior of one quantity as another quantity gets closer and closer to a specific value, typically a problematic one. All right, I'll catch you all in the next one. Cheers.